Presented by Caltech.
Finally, it's my honor to introduce today's keynote speaker. In addition to serving as president of the Institute, Thomas Rosenbaum is also the Sonia and William David Dow Presidential Chair and Professor of Physics. Prior to Caltech, President Rosenbaum served as provost for the University of Chicago for 7 years, where he had the responsibility for a broad range of intellectual endeavors across the sciences, arts, and professional schools. And he previously served as Vice President for Research for the Argonne National Laboratory. President Rosenbaum is an expert on the quantum mechanical nature of materials, the physics of electronic, magnetic, and optical materials at the atomic level that are best observed at temperatures near absolute zero. He was educated at Harvard and Princeton and performed research at Bell Labs, IBM Watson Research Center, and the University of Chicago before moving west. He is an elected fellow of the American Physical Society, the American Association for the Advancement of Science, and the American Academy of Arts and Sciences. Please join me in welcoming Professor Rosenbaum.
Thank you, Jan. I very much appreciate the introduction. I give a fair amount of talks, of course, as president, but usually when I'm introduced and being someone who knows something about quantum mechanical nature of materials, I reassure the audience that I'm not going to give a physics lecture. In this case, of course, I have the pleasure of giving a physics lecture. So I'm very grateful for that opportunity. So today I want to talk about using quantum mechanics to solve hard computational problems. Or the subtitle of this is Why Climb Mountains When You Can Tunnel Through Them. And I want to talk about the applications of these notions to problems that range all the way from magnets, which is the experimental system I'll tell you about, to proteins. And the idea is that if you start at the top of a mountain, say you're a ball at the top of the mountain, you want to get to the bottom because it's a lower energy state, you roll down the hill and you get into a valley. But what happens if there's a deeper valley here? How do you get there? Do you jump over, climb over the mountain, which is the classical sort of notion, usually assisted by some sort of thermal process, or can you tunnel through the mountain, which is where the quantum mechanics comes into play? There are numbers of ways to tunnel. One of them is the brute force solution. This is actually one of my favorite covers for a textbook, Introduction to Error Analysis. This is at the Gare du Nord, where obviously the tunneling was quite effective, if even not intended. But there are other more elegant ways, shall we say, and for those of you old enough to remember George Gamoff's Mr. Tompkins, who was a retiring, timid bank clerk with a very good imagination. He's sitting here in his living room with friends saying, how long have I to wait until a car will leak out through the wall of, let us say, a brick garage, showing up in the middle of his living room? Now, of course, objects as large as automobiles don't actually tunnel, except as seen through the error analysis approach. But if you're an electron with a much smaller mass, and hence a much smaller momentum, you can have an uncertainty in your position which allows the electron to pop through a barrier. And those are the sorts of processes we want to talk about. The first person who really talked in depth about using these sorts of ideas in terms of computation was Richard Feynman. We can give up on our rule about what the computer was. We can say, let the computer itself be built of quantum mechanical elements which obey quantum mechanical laws. This was in a keynote address here in 1981. And I want to try to explore this a bit today in our discussion. and think about it in the way that Feynman put this together. So in some ways, this is a process flow chart, if you will, for computation following what Feynman's talking about. So you have some sort of input, some sort of problem you want to solve. You can have classical processes or quantum processes. And quantum's, in Feynman's case, he's talking about looking at quantum elements, which will simulate the world quantum mechanically. You do your computation, and you get some sort of output. Of course, that output, if you're going to read it, has collapsed the quantum mechanics. It's now a classical kind of result, even though it's flowed from a quantum process, and then you print it out. I'm going to tell you today about a magnetic system. It sounds horrible, lithium homeoyttrium tetrafluoride, but it is basically just a bunch of electron spins, little magnets, that are distributed in a material. And the analog here is that I have some sort of wave function that describes all these spins, some sort of description of the placement and interaction of these little magnets. I go through, and this material is particularly nice because I can turn a knob and I can tune it classically. That is, I can change temperature, and I can take a quantum knob, and I can tune it using a magnetic field where I increase the tunneling, the ability to pop through those barriers independently. And I wind up in a final state. I have an initial state, a final state, and then I have to read it. And I'm going to read it with something called the magnetic susceptibility. But before we get to this description of these kinds of experiments, I want to back up. And I want to talk about the kind of background that I hope will make clear how the quantum mechanics enters. Okay, so I want to start with, and for those of you who are physicists, I apologize for backing up all the way this way, but talk about particle-wave duality, which is what you need to think about tunneling. Then I want to step aside a little and talk about these so-called hard problems. How do you arrange transistors on a circuit board? How do you fold proteins? Why are magnets interesting materials to look at in this context? And then I want to bring the two strands together and talk about quantum speedup. The fact is, by using quantum mechanics, you can do these calculations faster. So I want to talk about that and the limitations, and talk about this real system, this magnetic system, and talk about computer algorithms which use the same sort of techniques. And finally, my job as president is kind of quantum mechanical too. So I'm happy to take your questions in the Q&A about the university, the institute, about going through that. Okay, so let's start now with the first part, which is particle-wave duality. So the simplest experiment is just a classical one, which is to look at some light waves. You have a double slit, that is a barrier with two holes in it. The waves then interfere and give you a diffraction pattern, okay? And so this is what it looks like. They're dark bands and light bands. So if I shine a laser through the barrier and I look on the wall, this is what I'm going to see. Or if you take a CD and you tilt it the right way and look at it in the light, you'll see this sort of pattern, okay? So this is the interference. The peaks of the waves interfere constructively and give you the bright bands, and the peaks and troughs interfere destructively and give you zeros. Okay? The remarkable thing is you can do the same experiment with electrons, particles, right? Point particles, electrons, but they behave like waves. So I take some electrons, I have a double slit, and I have a screen, and I send them through, and I start recording on the screen what happens. So I go from here, A, B, C, D. You see I have a few coming through, a few more, individual electrons, accumulating more. And when I get a lot of them, all of a sudden I see that they're not actually randomly distributed. They're interfering like waves with light bands and dark bands, constructive interference, destructive interference. Okay? So this came from ideas of de Broglie. Going back to Mr. Tompkins, it reminded him of the railway station platform. Here we have the interference with our gazelles, and some very quantum mechanically astute lions who know exactly where to stand because they know where the constructive interference is of the gazelles. Okay, so de Broglie, who received the Nobel Prize for this, talked about the correspondence that material particles possess wave and particle properties, the correspondence of waves in a pond to electron waves in a metal. This is an experiment by Don Eigler at IBM, which is I guess 20 years ago. These are a bunch of iron atoms sitting on a copper surface, and the electrons here basically reflect back and forth in this elliptical figure that they're put on. These are individual iron atoms, and you can see the waves and the way they interfere, just like you see waves on a pond, even though those are electrons. Why am I telling you about all this in the context of the tunneling? Because this is, in some sense, if you'll forgive me, what an electron looks like. Okay, it's a point particle, but it's really described by a probability distribution, which is its wave function. So it really has a probability of being most probably here, but then there's some probability that'll be in other places because it's a wave. It has a waveform to it. And if I now take this electron and I put it up against a mountain, against the wall from Mr. Tompkins' garage to his living room, if the wave function is spread far enough out, there's some probability that actually it's going to show up on the other side of the barrier. And that's involved in this tunneling process. And I want to harness that ability to get through mountains, narrow mountains, not really broad ones because they'll get blocked, where I can't climb over the top. Okay, so we want to attack these optimization problems with quantum mechanics. And what we usually talk about in that concept is this diagram, which I sketched on the introductory graph, which is the free energy. You know what energy is. Free energy is just the combination of the entropy and the energy, to talk about the state of the system. And this somewhat mysterious term of configuration. Okay, so the configuration are the ways the system can be set up. So let me give you some examples. Okay, the most famous one of these probably is the traveling salesman problem. The traveling salesman problem is I have a salesman. Salesman has to go to a number of cities. What is the optimal route that the salesman can take? Okay, so you can use, let's use in this case, a salesman who has the distinction of going to only capitals of all the states, because this is the map I could find. Okay, in the United States, and let's minimize, the energy is the total amount of gasoline that's burned. Okay, so that's it. So a configuration here would be the salesman could say go all the way around the top and the bottom around the edge and then go like this and then loop around. That would be one configuration, one route, and it has a certain amount of gasoline burned. Now maybe I could also go the same way, except instead of going here, go up there and down and come back around. That would be another configuration that is close by on the configuration space, right? That would be one where I've just moved a little bit along this axis, but I'll have a slightly different energy, either up or down. Okay? Now I could try something really different that's on the other side of the configuration space. That is, I could go up and down like this. And I can compare the energies, and some of them will have very high energies, some will have low energies, and I'll trace that out. What is appealing about quantum mechanics in this case is that if I could do a calculation quantum mechanically, instead of the classical way I'm telling you now, which is to look at one configuration, one energy, another configuration, another energy, and go across, is that I can superpose all of these so the salesman, this quantum mechanical salesman, is traversing every path simultaneously. And then I can do the calculation, in principle, if I could do that, much faster to understand where the minimum is in that distribution. Okay? So another hard problem like this is circuit optimization. You know, and this is just the 50th anniversary of Moore's Law. It was a celebration up in San Francisco last week, earlier this week. The number of transistors on a chip is doubling every couple of years. And how do you wire them together in the most efficient way? Think of all the possibilities that you could have in that fashion. It's a hard problem that you have to solve. Protein folding is another one. This is a mouse protein, I think. And the idea here is that you have some sort of form where it's unwound, and to be functional, it has to fold back into its proper configuration for biological utility. If it tried every possible path, it would never get there in the time required to do anything useful. Okay, so there's still a bit of a mystery as how it follows its way through the energy surface to get to a state for biological utility. Okay, magnets. So let me talk about magnets and why magnets are good substrates on which to perform these experiments and learn something generally about this. So a ferromagnet, these are spins here, little bar magnets, north-south. Electron spins are like this. It's a quantum mechanical property of an electron. In a ferromagnet, piece of iron, all the spins, all the little dipoles are pointed up, or all of them are pointed down. In an antiferromagnet, they alternate, up, down, up, down, up, down. Okay? These are relatively simple states. You can predict. If I have a spin here and another spin here, I know what they're going to be. They're both going to be pointing up. If I have a spin here and a spin here, I know they're anti-aligned. A spin here and here, they're aligned, and so on. So the description of the final state is a simple one. It's much harder if there's a little disorder. If I mix ferromagnetic and antiferromagnetic bonds. So I have some spins that want to point in the same direction, some that want to point in opposite directions. So why is this hard to predict where the system wants to go? It's because of something called frustration. This is actually the scientific term. It is also a representation sometimes of doing experiments on these materials because they can take days to equilibrate. So here's the Gedanken experiment. I have a triangle, and on each vertex I'm going to put a spin, and the spins are aligned antiferromagnetically. That is the spin here. Its next nearest neighbor wants to be pointing in the opposite direction. So let's start in the bottom left corner. I have a spin pointing up. Okay, which direction does this go? Well, you can see it goes down, right? Now what happens in this corner here? Well, this spin interaction, right, says it should go up. This spin here, it's supposed to be anti-aligned, says it should go down. It has equal energy to point up or down. It's frustrated because it can't satisfy all the constraints at the same time. And so I have two such states here of equal energy. Different configurations, same energy, equal minima. Now imagine that I take a thermodynamic number of spins, right? Avogadro's number of spins in a chunk of solid. Then, all of a sudden, imagine the number of possible configurations that this system can find, many of them having energies that are almost equivalent, some more favored. So how do I figure out what is the right configuration? So that's what the hard problem is. Okay, so let's bring these two strands together. We talked a bit about the fact that even point particles like electrons behave as waves and can tunnel. And we talked about the kind of problems we want to solve where we have complicated configurations. Okay, this is a picture of the material. This is the lithium homeoyttrium tetrafluoride. These are big single crystals. It's about 1 centimeter long. You can buy them. They're laser rods. They're relatively expensive, but buying them is a big thing, big help. The color is due to the holmium, the optical transitions in the holmium, which is the magnetic species. So that's the spin. And this is, again, the generic figure. I want to look at these various configurations which have to do with the frustration. This is a mix of ferromagnetic and anti-ferromagnetic bonds. That's the system. In a nice, beautiful insulator, which I showed you, the single crystal. So this is the phase diagram. This is temperature. Now we're looking at quantum mechanical effects which get washed out by thermal excitations. So this is in Kelvin. These are absolute numbers, absolute temperatures. So 0 Kelvin, which is impossible to reach, is minus 459 degrees Fahrenheit. And we're looking down to temperatures which are about 10,000th of a degree above that, which is what you'd use a dilution refrigerator for. It has a transition from a paramagnetic state to a ferromagnetic state because 44% of the sites are occupied at about 700 millikelvin. And now I can cool down into the lowest state, but this is a glassy sort of system because it actually doesn't only have ferromagnetic bonds, it has anti-ferromagnetic bonds. This is the quantum knob. And I'll talk a little bit about that later. But for now, let's just take this as a knob, which is physically a magnetic field that lets me increase the tunneling. And what I want to ask is I want to compare what happens when I cool down with only thermal excitations. That is, I can only climb over the top of the mountain. And then I add some tunneling at the end. Okay, so then I can tunnel just when I get to very low temperatures, versus putting on the tunneling from the beginning, having lots of tunneling all the time, and then taking it off at the lowest temperatures. And I want to come to the same state. I can do it here, I can do it here, I can do it here, I can do it here. And I want to ask, do I get to the same place? And I'm going to call this the classical route, mostly dominated by going over the mountain. And I'm going to call this the quantum route, where most of my behavior activity is going through the mountain. And I want to ask, A, do I get to the same place? And B, how fast do I get there? Does quantum mechanics make any difference in solving the problem? Now, the problem here is not a programmable problem. The problem is the system starts in a particular state, and it ends in a different state. So it does its own computation. But if I put in lots of tunneling, it's doing a quantum computation. These are quantum mechanical spins that are dominated by the quantum mechanical interactions. Okay? So here's the data. Here's this figure again. Let's just look at what happens if I just go at relatively high temperature for the material to point A. Everything looks the same, but what am I plotting? I'm plotting the susceptibility. That is, I take a little magnetic field and I twiddle the system like this, and I interrogate the spin, and I say, where are you? Are you responding? And I do it as a function of frequency, and I'm asking at 10,000 hertz, at 1,000 hertz, at 100 hertz, this is logarithmic, 10, 1 hertz, 1 time a second, are you responding? So it's telling me about which spins can react, which spins are free, where is the response of the system maximized, okay? Now, this is a ferromagnet at the end of the day, although it's having trouble getting there, so its susceptibility wants to get big. That's the ground state. It will diverge. It will go to infinity over the period of years. But nothing happens here because basically the thermal temperature, the classical effects are so large because I'm not very high on the quantum axis that it all looks the same. Let me look here. This is the unordered state. The spins are just thermally jumping around, but I have a large amount of field. This is just a sanity check. Nothing's different either. Okay, so you just want to, it's an experimental check that when I'm not in the ordered state, nothing looks different. Let's go to the lowest temperatures where I have the highest transverse fields. That's point C here. What you see is things look very different. When I do quantum mechanics, in fact, I get to a different state. Okay? I'm getting closer to the ground state, which is the lowest dip here, okay? Because I'm heading over longer times, lower frequencies, to a point which is now going to diverge. Even more interesting, if we look at this, and this is just a blow-up of that, is that the onset to get to take off, to find the state, to do the computation, is much faster. Okay, this is hertz, so this is short times, high frequencies. It's about a factor of 30 times faster. So I can speed up my system by putting in quantum mechanics by about a factor of 30. And I can start the calculation, I can get closer to the lowest energy state. I'm not there, I'd have to wait too long, but I'm able, in fact, to speed up the system. And in fact, potentially, what I've done is I've wound up getting through one of these barriers so I can get down here. It may never get there classically. Okay. This is a great thing. It appears to be some kind of wireless technology. I haven't told you what the wires are. I've given you the result. I haven't talked about why does the quantum mechanics work better. And that's very interesting. It has to do with the fact that I can actually analyze the data as a function of temperature. I won't do it for you here in a kind of formalism, mathematical formalism, and I can figure out how many spins are flipping simultaneously. And so what's happening in this material is that, again, I have a block of spins that's about 10 or 12 spins that quantum mechanically together tunnel through that barrier. So I don't have to thermally excite an individual spin over the mountain one at a time, but in fact I can describe the results mathematically with flipping a manifold of spins, few on the side. This is a three-dimensional system, a little block of about 10 spins going through. And that's what the actual physics is of the quantum speedup. Okay. One can do this on a computer. There are ways to do quantum Monte Carlo, it's called. Monte Carlo, because you take random distributions. And so what this is a computer simulation, which is not done by us. These are the number of computer steps, Monte Carlo steps. This is the energy. This is the classical anneal. This is the quantum anneal. This is a two-dimensional version of the experimental system I was showing you. It's actually the Ising model in transverse magnetic field, which is closely related to some of Professor Smirnov's work. And what you can see is that I get to a lower energy state here, quantum mechanically, the open circles, and I'm coming at a different slope. I'm doing it faster. That's the good news. The bad news is you see this is a log-log plot, which means a straight line is a power law. So I'm getting some increase, but it's not an exponential solution. So it may never be fast enough to actually solve some of these really hard problems, which is kind of the holy grail. Can you get exponentially faster? Okay. As I mentioned, I'm telling you about results on a system that's doing its own calculation. Okay, so finding the ground state is doing its own calculation. Wouldn't it be wonderful if we could program this system and solve a different problem? I mean, that's a much more interesting quantum computation problem. And we've made some progress that way. A lot of people are working in this general field. They're working on things called Josephson junctions, which are superconducting quantum bits. They're working on cold atoms and traps. There are already some one-by-one built quantum computers, if you will, with 6 or 7 qubits, 10 qubits. To make a big quantum computer is not there yet. And there are lots of approaches. The beauty of this material, of course, is I have 10 to the 23rd bits. It's just I can't program it. So the question is, how can I program it potentially? And that is, what happens if instead of taking 44% of the sites occupied by spins, I just sprinkle in spins. So if I threw pennies on the floor and just randomly tossed them around, they wouldn't form a nice lattice, a nice crystal structure with even separation. They'd cluster, right? Randomly, some of them would be, you'd have a pile of 3 or 4 in one place, and 1 here, and 6 here, and so on. So we do the same thing with the spins. And we get regions which are close enough together that they're actually coherent quantum mechanically. Okay? And the physics of this is really interesting, is that I have these 2 spins, and I put on a field in this direction, but these 2 spins, they're called Ising spins, can only point up and down. They can't go to the side. And what the field does is it actually mixes the states so that my ground state is no longer the spin pointing up or spin pointing down, which I showed you in the picture, but is an admixture of the 2, the superposition of up and down. That's the quantum mechanics. Okay, and we'll skip that. And I can, in fact, look at these local regions, and I can do the same thing I did before with the magnetic susceptibility, but I can drive them really hard with high amplitude, and I can, in fact, burn holes in the response. And what that means is that these spins are now responding in those local regions, and they're responding labeled by frequency. And I can change the frequency and look at different regions of spins, and I can encode information. So there's some hope of taking advantage of this. The physics looks something like this diagram. I have these small regions, these clusters of spins, a lot of them then both pointing up and pointing down for long periods of time until I read them out, as Feynman suggested. Okay, and the most recent stuff we've done, and this is the end of the physics part here, is that you can now, because these are quantum mechanical, if you separate them from the environment, you can actually amplify these effects. And so what you do is you take your crystal, it physically sits in this refrigerator, which gets down near absolute 0, and you just make the connections stronger or weaker, and you can make it more or less quantum mechanical. Okay. So the summary is looking at this problem of tunneling through surfaces. What you find out, you get from here to there faster. You actually can find through this quantum annealing different minima than thermal annealing, which is important because if you want to figure out what the solution is, what the configuration is, say for connecting your transistors on your chip, you want to be able, even if it's marginally lower energy, marginally more efficient, to be able to investigate that set of configurations, which you may never get to otherwise. And there's some hope when you go to the dilute limit, so-called spin-liquid limit, that you can, in fact, think about how to reconcile physical systems to Feynman's vision of what a quantum computer can be. So as I tell my students and work, stick to it. There's a future in cryogenics, and this work has benefited enormously from a number of students over the years who are listed here, and Gabe Epley, who's my collaborator, formerly in London, now in Switzerland. So thank you very much for your attention. I'm happy to take any questions.